Okay, so let's talk about the rest of the motors. There are just a few stuff that you need to take note of a stepper motor. Alright, the range of a stepper motors I would assume is that talking about the size of the motor, alright, and the weight of the motor and the torque that it can actually hold. Alright, what it means by the holding torque is I think is that the holding torque I think is that you put in a weight on the motor itself, as you can see. I can't show you with the arrow because over here internet my arrow cannot show you. Alright, but over here at least you can see that what I'm shaking over here right now. Alright, take a look. Alright, your stepper motor actually ties down with a weight. Alright, I think I just copy the picture lah, macam only. Alright, so over here your rotor over here, alright, you're gonna tie down with a weight. Alright, so the holding torque is that how much weight can you hold onto your motor. Alright, so this is your motor, or you have a head. So how much weight can you hold onto the head itself? Alright, so this is just the holding torque that is able to, it is saying, yeah, something like that. And the holding torque is one of the key issues when you decide a motor. Okay, so whenever you talk about motor, please talk about the holding torque. Please look at the holding torque, look at the signs, at the specifications, so that you can understand how the motors will actually look like. Alright, things like that. Alright, so a bigger stepper means that I think you're gonna have a more power. Alright, more power, so that for example, like you can drive linear. Okay, sorry, bigger stepper I think is to drive more power lah, I think, to flatter pancake motor. So I think it is really big torque. Alright, so you have a high torque, so that you can actually provide a very huge force. Nonetheless, you can also have a linear stepper motor. Alright, this linear is actually to drive a screw, because when you have a motor over here, so you have this turning, so you connect your screw over here. So as you can see, when you turn your motor, it is spinning in this direction. Alright, so then your screw will actually go into the wall or whatever. So it's a linear thing, alright, which turn your rotary into linear motions. So this is how one of the motor is working. So this is the definition of a linear stepper motor. And over here this sentence says that it is not easy to actually keep track it is easy to keep track of the number of steps the motor has taken, but how do you know the absolute position of the object being moved? So the absolute position of because you keep on turning you keep on turning, so how do you know that absolutely where is the position of the object that is being turned? Alright, so in practical system you may need a reset sequence where the motor is driven to one end of its range detected by a separate sensor. So you may have a motor over here, and this thing keeps on turning. Alright, it keeps on turning, but over here you may have a mark over here, and then this mark over here as a sensor. So no matter how many times you touch this sensor, whenever you pass this mark, or the sensor will beep once, and then you monitor the position of your object that is turning, things like that. Alright, so for example, if you have this thing over here and you keep on turning, alright, so over here once you reach this point, alright, the sensor will taking one, and then once you turn another one, the sensor will take in the second pulse, the third one, the sensor will take in another one, so you know the position of where you are and things like that. Alright, hope that you kind of get that clear. So this middle one is where the motor is turning lah. So these are your coils, if you happen that you want to go into more details. Alright, so I think you get what I mean already lah. Alright, so this is something like a range of your stepper motors, and most likely I think it's talking about the holding torque and the position of your stepper motor. Alright, or position of your object that you are moving. Okay, next, stepper motor, or you may also have other motors. So it says that steppers are not the only motors, so you may have other motors. Okay, but generally stepper motors are very convenient because of their natural digital action, but they are not the other types of motors. But they are not the only type of motors available. The reason is natural digital action is because we can use pulses, alright, the waveform to actually generate our motor, or to increase or to decrease our motor, we can use this waveform easily. Alright, so therefore it is very popular for stepper motor to be utilized in many industry. However, most other types of motor will require an additional sensor for position, so you need to know your position of your object that is being moved, so that you at least you know that when you spin, your object wouldn't go into other positions that you don't want it to be, or at least are the more precise accuracy things that you, because for example, if you are turning, alright, then if your object is over here, alright, this is, how do I say it? So for example, you have this motor over here, alright, then you connect something over here, alright, so when you turn, alright, you want it to actually be within this particular region, the radius, alright, so because sometimes you may have vibrations all over, alright, so you want it to keep within a certain perimeter, which is the perimeter defined over here, this circular one. So it happened that one time if you vibrate and maybe your position will actually moved over here, then it's not considered safe or something. And these are the things that will cause troubles and things like that. So you need to know the position of your objects that are being moved and things like that. So you'll talk about control, dynamics and control what we have been studying lah, alright. So that the system ends up in the desired position that you want and things like that. So you talk about control theory. Alright, and last part is slight points to watch is that it is easy to get very small, or it's not easy. He say I don't think it's easy to get very small stepper motor. Alright, so small stepper motor means that one step, alright, is you turn it for a very small precise step instead of a big step. Big step I think is like this. Alright, so I think the small step means it's turning in a very precise manner. Alright, so if you don't know what I mean, this thing over here is the one that I'll show you. Where am I? Yeah, this one over here. Okay, so over here, if it's a small step, alright, you'll be very sensitive. You'll actually move towards the side only. Alright, you'll move in a very small angle. If it's a big step, you'll move in a very big angle. Well, you'll straight away move here, you see, and then next step you'll move back to this position. Alright, that's why I think I'm be wrong lah, but this is how I understand this thing. Alright, so because the construction is very complicated, because you will require more coils, because over here you have 4 coils. Alright, so you have one set of coils, 2 set, 3 set, and 4th set. So over here your precision, your stepper is 4 steppers, I think, I don't know, but if you have more steps, this means that you have more sets of coils. And then if you remember, one set of coils requires this type of thing to generate a north-south pole. So if you have more set of coils, then you need to design the wiring in a more neater way and things like that, which takes in a lot of time and efforts. So therefore this is what it's trying to say, the construction is pretty complicated. Alright, so therefore simple DC motors can be made smaller in model vehicles, for instance. I don't know what is it, but yeah, anyway. And take note that most motors draw a relatively large current, so you need to have a big driver and a good power supply to handle the load that you want. Alright, the load means your large current, okay? And stepper motors draw a high current when they are holding rather than rotating. Alright, so no back in EMF. So is it good or bad? I don't know. Alright, but it draws more current is because when it is holding, means that it is not moving. The current itself takes in many current. Alright, the coils itself have many currents. This is the coil, this is the coil. So each of the coil take in many current if it's not turning. So if it's turning, if it's rotating, then you actually take in lesser current, I think, for some reason, because it's turning, so you'll lose some of the power to the current power to rotate the stuff and things like that. Alright, so yeah, I'll leave you to think about it. And if you want to run the motor fast, stepper motors must be accelerated gradually, alright, because of the limited torque available. Alright, and this is controlled by the stepping frequency, so you need to control the frequency, and therefore the frequency must be a variable to control your stuff. Alright, repeat again over here. I think I am wrong. It's because you require a large current, alright, in order to drive your load. Alright, the load is whatever weight that you are looking at. Alright, so you require a large current, so you need to make sure that your driver and power supply is large so that you can actually drive whatever load that you want to drive. So if you connect your motor in this way, alright, and if you connect it to a load, for example this fan blade, you ensure that in order for this fan blade to turn, you require a good amount of power supply and the driver itself. Alright, so such that the fan will rotate and things like that. Alright, he didn't actually go through this part, alright, but I think this one over here is telling you that at first it start up a little bit and then you'll start to rotate. So this portion over here tells you that you require a certain time. So this part tells you that you need to accelerate gradually. Alright, so your power, you have to accelerate gradually before you reach your rotation, your rotary speed, your maximum rotary speed. So over here, this straight line over here is your maximum rotary speed. So it's a pull out rate, maximum rate in motion. Alright, so once you start to slow down, then you gradually slow down and eventually you'll become idle. Alright, so idling is always this thing, one straight line over here. So if you want to pull out, then you increase the rotation slowly up to a certain point where it's highest, and then if you want to decrease, you will decrease slowly. And then I think that's all it is for this thing. And the maximum rate from rest and maximum rate in motion is, I think, is the power. I think the rate of the power or the frequency supplying into the rotor. So by standard, I think this is the amplitude. So if you didn't spin anything, alright, you by default you have a certain amplitude already. You have certain waveform that is applying. Then up to a point where you want to supply a rotary motion, you spec up again and continue to go up to a certain point. I don't know what I'm drawing also lah. But anyway, this is all I know for these things. Alright, so this is the part for motors. I'll see you in the ADC part later on. So see you there.